Hey everyone, and welcome to this explainer. Today we're focusing our attention on the totally fascinating internal architecture of high-performance liquid chromatography, or as it's way more commonly known in the scientific community, HPLC. If you've ever found yourself wondering how on earth scientists isolate highly specific molecules for pharmaceuticals, environmental testing, or really complex chemical analysis, well, the answer almost always involves this incredibly clever piece of technology. But before we get into the nuts and bolts of the mechanics, I want you to think about this for a second. How do you perfectly separate the literally invisible components of a liquid? It's a wildly complex problem, right? You've got a mixture where everything is blended absolutely seamlessly at the molecular level, and you somehow need to pull it all apart into distinct, measurable, completely pure components. Doing that requires forcing a liquid phase through a stationary phase with immense pinpoint precision. So how does a machine actually pull that off? Okay, let's dive right in. The absolute best way to conceptualize the general scheme of an HPLC system is to think about something you probably have sitting in your living room right now. The source material draws this brilliant analogy. An HPLC is exactly like a modular hi-fi audio system. Think about it. A hi-fi system has a turntable, an amplifier, maybe an equalizer, and speakers. They're totally independent entities, yet they're completely interrelated, harmonizing together to produce a final result, which is the music. An HPLC system operates on that exact same principle. It relies on several distinct components with highly defined functions that are typically inserted into a common frame to form a single integrated unit. Section 1. The network of tubes, the veins of the system. To really appreciate the physical environment connecting these modular parts, we first have to wrap our heads around the microscale we're dealing with. The interconnected transfer tubing between the various components of the HPLC system has a remarkably tiny internal diameter. We're talking just 0.1 millimeters. That is incredibly fine, literally about the thickness of a human hair. Moving liquids through a tube that narrow is absolutely no small feat, and it really sets the stage for the intense physical forces at play inside the machine. Now, back in the day, these narrow transfer tubes were traditionally constructed out of stainless steel just to handle that demanding environment. But, material science has evolved a lot. Today, these tubes can also be made of PEEK, which stands for polyether ether ketone. Try saying that 3 times fast. PEEK is a colored flexible polymer. And the great thing is, not only is it less expensive to fabricate than traditional stainless steel, but its flexibility makes it so much easier to work with when you're physically configuring all those interconnected modules of the system. But hey, don't let the phrase flexible polymer fool you into thinking this stuff is delicate. What is truly awe-inspiring here is that this PEEK tubing remains incredibly resilient. It easily withstands common solvents under staggeringly elevated pressures, up to 350 bar. Just to put that into perspective, that's hundreds of times the pressure of the air in your car tires. These tiny 0.1 millimeter tubes handle this continuous, massive stress while relentlessly shuttling chemical samples back and forth. Section 2. Mapping the HPLC schematic, the hi-fi journey. So now that we understand the modular nature of the system and those high-pressure veins connecting the whole shebang, it's time to actually map the journey. The core schematic of an HPLC system brilliantly transforms this abstract idea of chemical separation into a concrete visual map. It shows exactly how each modular component stacks together sequentially to form a continuous pathway that ultimately ends up at the computer. Let's play tour guide for a minute and actually trace the mobile phase step by step through the process. First up, we start with the solvents, acting as our mobile phase, which pass through a degassing system. Second, the pump aggressively drives this liquid forward, creating that massive pressure we just talked about. Third, the actual sample is introduced right at the injector. Fourth, the whole mixture travels into the thermostated column, and that's where the real magic, the actual chemical separation, takes place. And finally, step 5. Those newly separated components hit the detector, which immediately sends the final analytical data straight to the computer. Section 3. The physics of flow. Inside the column. Okay, let's zoom way in on the actual physics governing this microscopic environment. The movement of the fluid inside that tiny column follows a principle called Poissonier's law. This law basically dictates the nature of laminar flow. You see, in a tiny tube, the fluid doesn't just rush through all at the exact same speed like a solid block. Actually, the velocity of the mobile phase is at its absolute maximum, right in the very dead center of the tube. As you move outward toward the edges, friction starts taking over, and the velocity rapidly drops to 0 right at the wall. And here's why that specific bit of physics actually matters so much. Maintaining a low flow rate of the mobile phase is kind of the ultimate secret to the system's performance. When the flow rate is low, it perfectly maintains that laminar flow dictated by Poiseuille's law. This carefully controlled movement minimizes the dispersion, or the spreading out, of the compounds as they travel through the instrument. And why is that absolutely crucial? Well, because minimizing that dispersion directly improves the detection limits. It allows the machine to reliably identify even the absolute most microscopic, faintest traces of a chemical. So this brings us right back to our core definition, really tying the whole room together. HPLC systems are composed of several components with defined functions that represent independent yet interrelated entities. We've just seen how the high-pressure pumps, the 0.1 millimeter peak tubing, the injector, and the column all have entirely different physical jobs to do. Yet they all harmonize perfectly, literally just like that hi-fi stereo playing a record, to maintain ideal flow dynamics and achieve one singular unified purpose: flawless chemical analysis. As we wrap up this explainer, I really want to leave you with a final thought to ponder. We've seen exactly how pushing liquids through unimaginably tiny tubes at 350 bar unlocks this entirely invisible chemical world. So think about this. How could further optimizing these tiny, high-pressure flow dynamics completely change the future of chemical analysis, or radically speed up how fast we develop life-saving pharmaceuticals? It's a huge question, and it's exactly what chemists and engineers are working to answer right now. Thank you so much for joining me today, and keep exploring the science all around you.